Good afternoon, class. Here's statistics, practice test number 2, module 2, covering chapters 4 and 5. Here's chapter 5, discrete probability distributions. So here's a pledge. I repeat, we've seen this a few times. I pledge on my honor that I will neither give nor receive unauthorized assistance, so on and so forth. Of course, you may use formula sheet, tables, and a graphing calculator. Does the table describe probability distribution? What is the random variable? What are its possible values? And are its values numerical? So those are actually the criteria. So X represents the number of gears, and P of X is the probability. This is called a probability distribution. The variable X, which is the number of gears in the three birds, 0, 1, 2, 3, number of gears in three birds, is a numerical random variable, and its values describe probability. So that's one criteria. Number two, the summation of P of X must be 1. In other words, this column, probability, add them up, the sum must be 1. Now, in some instances, due to round of error, it may be not exactly 1, but it is close to 1, such as 1.00000001 or 0.999999. That's due to round of error. And finally, each value must be between 0 and 1. Each value of P of X is between 0 and 1. P of X is larger than or equal to 0, less than or equal to 1. So can it be 0? Yes. Can it be 1? Yes. Can it be negative? Absolutely not. Larger than 1? No. So those are the three characteristics, criteria that make up a probability distribution. So they are numerical, they are probability. These numbers must be between 0 and 1, and the sum must be 1. In a game, you pay 60 cents to select a 4-digit number. If you win by selecting the correct 4-digit number, you collect $3,000. How many different selections are possible? Well, there is no restriction. It's 4 digits, and we have 0 to 9, 10 numbers. So there are 10 possible numbers in 4 places. So 10 to the power of 4 or 10,000. Because the numbers can repeat, there is no restriction. What is the probability of winning? By definition, probability of winning is N of winning over N of S. So N of S is 10,000. There are 10,000 different ways. How many ways can we win? Just one way. So 1 out of 10,000. If you win, what is your net profit? Well, here's the money we receive, and here's the money we spend. So net profit is money gained, which is $3,000, minus investment, or in this case, the cost of the game or the ticket. So the net profit is $2,999.40. Write the probability distribution of net profit if you win. So we want to make up the distribution, probability distribution. So we have number of $3,000 winners, losers, total, net gain, and P of X. So over here, there's only one person that, or one ticket that can win $3,000, and the rest won't. The rest mean total of 10,000. So total is 10,000 here. This is 1, the rest of it, that means 9,999 is here. Now, the winner gets this much, but the rest who play and they do not win, we call them losers, would be the 60 cents that they spent, so negative 0.60. What is the probability here? The number over total. Of course, this is the answer for the first one, 1 over 10,000, or 0.0001. Over here is the rest of it. This number divided by 10,000. And of course, as you can see, they must add up to 1, and they do. So that's the probability distribution table that we made up. Now, find the expected value and interpret. This is the table we made up in the previous page. I'm going to remind you the formula for a discrete random variable. Mu is summation of x p of x. Sigma squared is summation of x squared p of x minus mu squared. And it can be shown that it's x minus mu quantity squared times p of x. So having said that, we want to come up with the expected value mu, which is summation of x p of x. So this is the x group. This is the p of x. So we are going to make a column x p of x. So we're going to multiply these two numbers. We put them here. Then we multiply these two numbers. We put them here. Now we're going to add these two. And that is summation of x p of x or mu. So mu, or summation of x p of x, is negative 0.3. That means about 30 cents. Now, we also want to find the standard deviation. So we find this and we take a root. So the square root of that is the standard deviation. So to find x squared p of x, we're going to come up with x squared p of x here, which means square this number times this, and then square this number times this. That's the meaning of x squared p of x. We put it into calculator. Again, square this one times 0.0001, square this one times 0.9999. And now add the two. This is about summation, okay? So we are going to add the two. And now into this formula, we put this number minus mu, which is negative 0.3 quantity squared. Put it into a calculator. And this number is extremely close to 30. So it is important for this part, the interpretation, we have to calculate the sigma. What does it mean? The average is negative 0.3. The standard deviation is about 30. So everyone who plays on the average loses this much with this standard deviation. We're going to say, so on average, a player, all players, including the winner, on average, loses $0.3 or 30 cents per ticket with standard deviation of this number. We're going to take it to be $30. Because normally in the case of money, we go with 2 decimals. A pharmaceutical company receives large shipments of aspirin tablets. The acceptance sampling plan is to randomly select and test 24 tablets. The entire shipment is accepted if at most 2 tablets do not meet the required specifications. If a particular shipment of thousands of aspirin tablets actually has a 5% rate of defect, what is the probability that this whole shipment will be accepted? So let's see what we are dealing with here. It's important to understand we are dealing with binomial distribution because there are 2 outcomes. It's either defective or not. So that's a BD, binomial distribution. How many tablets? N. We're going to test N equals 24. What is the probability of defect? P is 0.05. Again, remember, P is the probability of success, but doesn't necessarily mean negative or positive connotation. That's important to understand. So reminding you of the binomial distribution, the formulas are as follows. P of x is n factorial over x factorial times n minus x factorial. This is combination of n choose x. P to the power of x, q to the power of n minus x. Mu is np, the average, the expected value. Sigma is square root of npq. As always, q equals 1 minus p. So what is a binomial distribution? Binomial experiment and probability distribution, PD short for probability distribution properties. Number one, we have n identical. That means fixed number of trials. Each repetition of the experiment is called a trial. Each has only two categories of outcomes, yes or no, good and bad, so on and so forth. Probability stays constant and they are independent trials. So having said that, if P is 0.05, first of all, Q is 1 minus that, making it 0.95. So into this formula, let's put everything that we have. In other words, replace the N with 24, P with 0.05, and Q with 0.95. So that would be the general idea. Now let's go back and read the question. The entire shipment is accepted if at most two tablets do not meet the requirement. That means probability of X less than or equal to 2. It's important to understand at least means less than or equal, which means X can be 0. Remember, this is discrete. This is countable. X can be 0, X can be 1, X can be 2. So we calculate probability of X equals 0 plus probability of X equals 1 plus probability of X equals 2. So into this, we replace the X with 0, we come up with an answer. 1, we come up with a different answer. 2, we come up with a different answer. We add all three. So if we want to do it by hand, we can do that. However, when you get to this point, you may use a technology as follows. So binomial distribution, second variable is binomial PDF NPX. Enter. If you enter N and P only, it gives you all probabilities from 0 to N and so forth. Therefore, we are going to do the following. Binomial CDF from 2. Number of trials, N is 24, P is 0.05, and X is 2. It goes all the way to 2, from 0 to 2, when you put that. That's how it calculates. So gives all probabilities from 0 to N when you go that route. And so CDF calculation, okay, results in this number, which is obviously same as this one. If you stop at 0, you change it to 1. Pretty straightforward. It is known that 70% of managers of all companies suffer from job-related stress. What is the probability that in a sample of 20 managers, exactly 8 suffer from job-related stress? And again, reminding you that we are dealing with a binomial distribution because there are two outcomes. Either they suffer from stress or they don't. N is 20, P is 0.7. So we are dealing with the binomial distribution, N is 20, P equals 0.7. Reminding you of the formula we wrote in the previous page. And into this, we replace the N with 20, P with 0.7, and of course, Q with 1 minus P, which is 0.3. So first we find Q, then we replace it here. Everything goes into this formula. For exactly 8, and because just one, just all you have to do, replace the x with 8, everybody. So we want probability of x being 8, replace the x with 8. There you have it. Uh, you can do it by hand, you can do it by a calculator. If we go with binomial, in this case, we go with binomial PDF because we want just one value. So n is 20, p is 0.7, and x is 8. Please distinguish between binomial PDF and CDF. Gives you this answer. We write it here. When we stop at 2, next to it is 8, we change it to 3. Again, you write all the decimals that are given just to be on the safe side, unless they tell you how many decimals, then you want to follow that. So we are looking at the same question, and we wrote the information we got from the previous page. Now, part B. At most, 8 suffer from job-related stress. So probability of X less than or equal to 8. So at most means this. So X can be 0, 1, 2, all the way to 8. So into this formula, if we were to do it by hand, we would replace the X with 0, then with 1, then with 2, all the way to 8, and add them up. That is the methodology. Of course, nobody expects you to do that by hand anymore. But understand the concept. So we will go with binomial CDF. N is 20, P is 0.7, and the X value is 8 because at most 8. So this is how it works, and we end up with this number, and we put it in here. If we stop, look at this one, 8, 1. 1 next to it is 6. If you stop at 1, it changes to 2. Again, you put all the digits that you have here, unless they ask you for a specific number of decimals. Having said that, what about at least 9 suffer from job-related stress? Probability of X larger than or equal to 9, which means probability of X equals 9, 10, and all the way to N, whatever it might be. So if we were to calculate this by hand, P of X equals 9 plus P of X equals 10, all the way to P of X equals 20, nobody expects you to do that. Now, how do we calculate this? We notice probability of X larger than or equal to 9 is the same as 1 minus probability of X less than or equal to 8, complementary even. Okay. So X less than or equal to 8 is complement of X larger than or equal to 9. And just in case, this is as far as discrete value, for discrete is the same as X less than 9. Okay. So having said that, it's the same thing. So we don't have to do much, 1 minus this number, because we already have this. And the answer is 0.99486. By the way, again, this one, I stopped at 3, next to it is 8, I changed it to 4. Okay. Same question, find the expected value. Mu is NP. N is 20, P is 0.7, and we end up with 14. Find the standard deviation. Sigma is square root of NPQ. We can find sigma squared. N is 20, P is 0.7, Q is 0.3. We get 4.2, and sigma is the square root of this number. Use a couple of decimals at least. Again, as far as the number of decimals, if they don't mention it, you write all the decimals. Would it be unusual to claim that 7 managers from this sample suffer from job-related stress? I hope you remember. According to empirical rule, mu plus minus 2 sigma. That's the usual, it's called. that will cover 95% of the data. So mu plus minus 2 sigma. The value of mu, we found it to be 14. And then we multiply this one by 2 and subtract from 14, add to 14. So 14 minus 2 times 2.05 as well as 14 plus 2 times 2.05. Here's the numbers. As far as unusual or usual, this is the usual range from 9.9 to 18.1 is usual. Is 7 a part of that? No. 7 is not an element. See, this means an element of, and this means not an element of. 7 doesn't belong to this uh, range of 9.9 to 18.1 because it doesn't, it becomes unusual. If it's in between, it is usual. Find the probability of a couple having at least one girl. We are assuming the probability of boys and girls is the same. Probability of at least one is 1 minus probability of none. And that means we are going to write 1 minus probability of none. That means probability of boys to the third power. It so happened, we are assuming they are the same. They may not be the same. I want to emphasize this. So whatever this number is to the third power, 3 boys, 1/2 to the third is 1/8. So 1 minus that 1/8 is 7/8. And if they ask for percentage, you change it accordingly. Here's one and you're done. Here's the second method. You can use binomial distribution. N is 3. Probability of girl is 0.5. Because remember, you need two things. You need N and P, P probability of success. And we want at least one X must be larger than or equal to 1. P and Q happen to be the same. X is 1, 2, 3 because we have 3 children. And so 1 is good, 2 is good, 3 is good. And again, you can put that into a binomial distribution and evaluate it, or 1 minus P of 0. So here's the binomial distribution formula. 1 minus P of 0 is easier. Instead of calculating 3 of them, you calculate 1 of them and subtract from 1. So you replace here the X with 0, the P and Q, both of them with 0.5. So N is 3. 3 factor over X factor, 3 minus X factor times 0.5 to the power of X times 0.5 to the power of 3 minus X. So plug in for 0. These two cancel each other. This is 1. 0.5 to the power of 0 is 1. So 0.5 to the third power, or 1/2 to the power of 3, which is 1/8. And 1 minus that gives you the same answer. By the way, it's extremely important to notice P of B is 1 minus P of G for P of 0. Okay, this is P of G, this is P of B. The reason I mentioned that, what if they are not the same? Okay, what if they're not the same? And so I'm going to explain that further in a moment. So 1 minus 0.5 quantity Q gives you the same answer as we had. So this was the second method. What I want to mention again, this is important. For example, if the probability of having, and normally in biology, it's more than 50%. Let's say it's 0.55. We're making numbers. And for boys, it's 0.45. That means over here, instead of 0.5, you have to put 0.55. Over here, instead of 0.5, you have to put 0.45. So it's important to know which one goes where. Okay. And in that case, over here, instead of 1/2 or 0.5, you would put 0.45. That's the idea. I want to make sure it's absolutely understood. If an alarm clock has a 0.9 probability of working on any given morning, what is the probability that it will not work? Well, complementary event, probability of A naught is 1 minus probability of A, or A bar, or complement, as you all remember. So probability of working, W is 0.9. Probability of W bar, that means not working, is 1 minus that. And obviously 1 minus 0.9 is simply 0.1, or 10%. What is the probability that two such alarm clocks will not work? Well, basically, the probability for the first one as well as the second one, okay? Probability of working, probability of an alarm working, W1 not, probability of an alarm not working, okay? And probability for each one working is 0.9, not working is 0.1. And so probability of W1 bar intersection W2 bar is probability of the first and second alarm not working. They are independent. Their product is the answer. So probability of W1 bar intersection W2 bar is probability of W1 bar times the probability of W2 bar, which is 0.1 times 0.1, or 0.01. So probability that one doesn't work is 10%, which is actually a large number. That's bad. But if we have two of them, there is 1% probability that two such alarm clocks will not work. And that's the concept of quality control that is used when things of that nature happen. What is the probability of being awakened if you have two such alarm clocks? The assumption is that uh, when one of them works, you wake up. That's the assumption. And this is the information from the previous page. Probability of working was 0.9, not working is 0.1, and for two of them not working is 0.01. So there are different methods. Method one, probability of being awakened is 1 minus probability of not being awakened. That means not working, 1 minus this number, and it's 0.99. So there is a 1% chance the two of them fail, and there's a 99% chance that they won't fail. When they don't fail, we wake up. Method two, addition method. Probability of A union B is probability of A plus probability of B minus probability of A intersection B. So probability of W1 union W2 is probability of W1, which is 0.9, plus probability of W2, which is again 0.9, minus probability of W1 intersection W2, which is 0.9, times 0.9, because they are independent. And if you do the math, this is 1.8. This is 0.81, and we get, again, the same answer, 99%, or 0.99. Method 3 is binomial distribution. N is 2. There are two alarm clocks. Probability of working is 0.9. And obviously, Q is 1 minus that. And we're going to use this formula. So into this formula goes N equals 2. P is 0.9. Q is 0.1. And probability of X larger than or equal to 1. Because 1, that means probability of X equals 1 plus probability of X equals 2. So into this formula, you have to put 1 and then 2 and add them up, or 1 minus probability of 0 is easier. So plug in 0 and subtract it from 1. When we do that, I hope you see that 0 factorial is 1, this is 2 factorial, so this is 1, this is also 1. So it's 0.1 squared, which is 0.01, 1 minus that, same answer, 0.99. Pretty straightforward, everybody. So, three methods. Okay, we've already calculated the probability that both of them fail. So the complementary event is the answer. You can use the addition method or binomial distribution. During an NFL season, there were 256 games played with 1,307 touchdowns scored. Poisson distribution we're going to use. What was the mean number of touchdowns, TD for short, scored in each game during the season? Round the answer to the nearest 0.0001. They are telling us how to do the rounding. Okay, that's important to understand. So first, let's discuss Poisson distribution. Poisson distribution. The probability of the event occurring X times over an interval. The interval can be time, distance, area, volume, or some similar unit. Is given by P of X is mu to the power of X e to the power minus mu over X factorial, where A is the base of a natural log 2.71828 and it continues indefinitely. Mu is the mean number of occurrences of the event in the interval, and the parameters are mu and sigma, where sigma is equal to square root of mu. Therefore, to calculate this, the mean number of touchdowns is number of touchdowns divided by the number of games. So how many touchdowns? 1,307. How many games? 256. And so here's the answer. And since we want 4 decimals, 1, 2, 3, 4, then number 4 changes to 5. By the way, number of games is a discrete value, is a countable value, is a natural number, it's a whole number. But then when you say on the average, it doesn't have to be. That's important to know. So as far as this formula is concerned, we are going to replace the mu with the number we just got. That's the Poisson distribution in general. On January 10, 2010, the Green Bay Packers and Arizona Cardinals played a playoff game in which there were 13 touchdowns scored. What is the probability that the random game would have that many or more touchdowns? So we want the probability of X larger than or equal to 13. So what does it mean? Probability of X equals 13 plus 14, 15, 16, and sky's the limit. So I hope you see that it's pretty difficult to do that. But if we go with a complementary event, it's the same as 1 minus probability of X less than or equal to 12. So you calculate this, which means if we want to do it one by one, you plug into this one, 0, 1, 2, so on and so forth. And you subtract it from 1. If you want to go with a technology such as a TI calculator, second variable is Poisson PDF, mu or lambda or X. By the way, in many texts, they use lambda instead of mu. Lambda represents the mu, okay? And so in this case, we're going to go with Poisson CDF for 12, okay? We're going to calculate this part, just the 12, and then subtract it from 1. So what we have here is lambda or mu is this number. Now, when you want to put it in here, you don't want to put the rounded one. You want to put as many decimals as possible, okay? X is 12, and enter or paste it. This is the answer for this part. Subtract it from 1, and that's the answer. And by the way, at this point, I'm going to just do the rounding here. 1, 2, 3, 4. Next to 4 is 0, so I'm going to keep it and I'm done. So again, a quick recap. This is how we find P of X. all you have to do, replace the mu with the value that you found here. E, uh, keep it as E is an exact answer, but roughly means 2.71826. You want probability of x larger than 13, which means probability of x equals 13 plus 14 plus 15 plus 16, and you keep on going. So obviously, the complementary event makes it easier to calculate. So I hope everybody's following that. So here's the table we want to fill up. The first column lists the number of touchdowns, 0, 1, 2, 3, 4, 5, and so on and so forth, in a game. This is filled already. The second column is for the predicted probability that a game chosen at random will have that many touchdowns scored. Calculate these values, round these values to the nearest 0.0001, that means 4 decimals. So we're going to put it here. And the third column is for your best prediction about the number of games during the season that had that many touchdowns scored. And round them, of course, this one has to be rounded to the whole number. So what do we mean by that? Let me quickly show you a couple of them, and then we'll take it from there. Having said that, we have a P of X equals this from the previous page. So let's start with 0. Let's replace the X with 0. And I hope you see that, of course, this is 1, this is 1. So e to that power, and that's the answer. And that's fine. If we go with Poisson PDF, lambda is 5.10546. As I said, put more decimals, x is 0, paste it. You get this answer. This is the answer that goes in here. But for this one, probability column times 256, right? Because there were 256. So you multiply this one by 256, and it will be here. So this number is this one, everyone. And we are going to go with 1, 2, 3, 4 decimals. 1, 2, 3, 4. This 0 changes to 1, okay, because they said 4 decimals. Over here, when we multiply these two, we get 1.55, and we change it to 2 because you have to go to a whole number. And you want to continue with that. So let's look at, for example, 1. So over here, we can put 1. So that's the number that was mentioned here. So this is the answer, but we rounded up. For the next one, in other words, into this formula, replace the x with 1. Into this formula, replace the x with 1, put it here, and then multiply it by 256, put it here, and round it. And so this number, 0.3095, and notice I'm rounding it because they said 4 decimals, 1, 2, 3, 4. Because it's 9, next to it is 5. I change this to 10, becomes 0.310. I multiply it by 256. I put it here, and 7.924 doesn't matter. 7.9, you round it to a whole number, becomes 8. You can do the rest of them as well. So into this formula, replace it with 2, 3, 4, and so forth. So for example, with 2, we have this number here. We want 4 decimals, 1, 2, 3, 4. 0 remains, and then times 256, 20.23. So this is 0.790, and we're going to continue. And round it to the nearest whole number, becomes 20. So 20.23, and rounding it gives us 20.